So we're going to do three things. We're going to talk about the motion of free fall and being a constant acceleration while in that motion. We're going to talk about displacement, velocity, and time, the three things we've been mentioning. And then we'll talk about different objects in free fall and how they compare. So let's start with the first slide here. So this is a great example. And this is a really simple example for you to consider mentally. You can take any object. I mean, I'm just going to take one of these. There we go. Incredible over here. Let's bounce as much. An incredible or any object that you can toss up and down. And when you think about what's happening to the object upon its path, there's a lot going on. A lot more than you'd actually expect or suspect prior to this. So this image here is a pool ball, but imagine you toss it up and it comes back down. That's it. That's the whole problem. And a lot is happening in that simple problem that just occurred. In me tossing this up and coming back down, there's so much going on. So let's talk about what's going on. On the right here, this is a graph of the object's velocity versus its time. Why does it start with a positive velocity? See where it starts up at 10 point something? Why does it start with a positive velocity, Will?
It's going like upwards. So
Perfect. That's it. Good. It starts by moving upwards. So I toss this object, which way to start? Upwards. Now, a lot of you know this. In order to move forward and then to move backward, what do you have to do at some point in time? Or to move up and then move down. What do you have to do at some point in time?
Stop moving.
Stop. You got to stop moving. When you're not moving, what's your velocity? Everybody.
0.
And take a look. Isn't there an x-intercept? And the x-intercept means the velocity is 0. So this is the top of the peak right here. So you should probably label these things, right? In the beginning, it's positive velocity because it's been tossed upward. The very beginning, circle that little piece. And as the year progresses, you're noticing I'm writing less and less in the notes, and I'm trying to demonstrate more for you guys. You got to take these little things down. So the beginning, there's positive velocity because it's tossed upward. The object then slows down until, as Joe said, it stops at the very top of its path. Well, that's where you see the 0 of the function. From your math class, you know that zeros of a function, or the x-intercepts, in this case it's called the t-intercept, really, it's the t-axis for time. But the intercept right here, that I'm pointing to, is when the object reaches the top of its path. Now, if I'm a student and I'm actually drawing this, or I'm writing this down, I would probably also write the following. I would write a little note right here. See where I'm pointing to? I would write a little note that says, object slowing down, because that's what's happening. The velocity is decreasing. A decreasing velocity means the object is slowing down. And then again, right here, I would write down that the object stops at the top of its path. Now, when it gets to the top of its path, start the problem over. Okay? Start the problem over. So now I want you to, and this is a tough thing to do, so I'm going to actually point it out to make sure we're all focused on this specifically. When the object is thrown upward, kind of like freeze your mind for a second when it gets to here. Okay? And begin the problem as if it was just dropped. Because that's physically what's happening, right? I toss this object straight upward. When it gets to the top of its path, it's got to stop, and then it starts to come back down. So at the very top of its path, we're here still. But the way I want you to think about this problem is not as an overall problem, but two little pieces. Okay? So on the way up is part 1. On the way down is part 2. So on the way down, we're looking from here down on our graph. Because at the top, it's got no velocity. So we're still here at this point. But then, notice what's happening to the velocity. Why is it becoming negative? Earlier we had a positive velocity when it was tossed. Why is it becoming negative now? What do you think?
It's going down.
Yeah, it's moving down. Simple enough, right? So on the way up, we know it's positive velocity slowing down. And remember the other day when we talked about velocity and acceleration, how you could have slowing down or speeding up? When the signs oppose each other, well, the velocity is positive, acceleration is pulling down, so it slows down, it gets to the top, it stops for that instantaneous moment, for that small amount of time, and then it starts to fall down. How many of you heard the saying before? I've heard this. If you drop like a penny from the Empire State Building, it'll go into someone's head. Or if you drop like something that's even light from a high enough altitude, it could cause a lot of devastation, if you will. What's going on? Why can that happen? As it travels further and further down. Why is that saying? It's not really accurate, by the way, but to some extreme, with some sense, it does make
Because
sense.
it's speeding up.
Yeah, it's speeding up in what direction, though?
Downward.
Yeah, in the downward direction. So the velocity is becoming greater and greater, but in the negative direction. From your first test, think back about speed and velocity. For those, a couple of you here this morning for extra help, we talked about speed and velocity. That's the difference here. the velocity is increasing but in the negative direction. So it's just speeding up. It's speeding up downward the whole time now. Now, why doesn't that really hold true, that saying about the penny or an object dropped? Anybody know a little more? Eventually, what happens to an object? There's a saying or a phrase that some people might know. Good. It hits terminal velocity. Now, you know the word. Do you know what it actually means? What's happening there?
It means like you can't go any faster than you reach like the maximum speed it can go.
That's it. Very good. Well done. It can't go any faster. It's still going to move. It's not going to stop. It's not just going to be falling and then it just stops out of nowhere. But it will eventually reach a velocity that it cannot exceed. Anybody know why? We're going to get to this really in like chapter 5 and 6, but just out of curiosity, what do you think? Isabella, then Joe?
Is it because of the weight of the object, or?
You're on the right track. The weight pulls it down. So you're on the right track. The weight is definitely used here. We need the other half of it. What does
It
it
could
also
also be because maybe the shape that's influencing like how fast it can go or how like where it has to stop.
Keep going. Keep going. The shape definitely affects
and,
it.
And if like there's like a lot of air resistance, then maybe you can't like go as fast. Something else.
That shape, right? So you guys have seen this before. This is a great time to do this actually. The answer here. So you've learned and you've heard in your physics and physics science class that all things fall at the same rate. But you know that's not true, right? With air resistance, things don't. Which is going to hit the ground first, obviously. Right? Clearly. I don't even have to actually do it. If I just let go of this, look how slow it goes. That reaches terminal velocity within like a millisecond. It's absurd. I mean, you drop this object and it's already, it's at terminal velocity. It's not getting any faster. Whereas the ball, it actually still gets faster on the way down. This reaches terminal velocity right away, like Joe said, because of the air resistance and because of the shape. Anything you want to add? Because I saw you had a hand up for this.
And because of gravity, gravity is only strong enough, you can't like blow you more than
And gravity is a limited value, is what he's saying. So your weight, or the gravitational pull, is set. It can't be greater than just a random value. So for example, when you say you weigh 150 pounds or 160 pounds, that's your weight. That's the force of gravity pulling you down. So eventually, this object gets balanced by the air resistance pushing up, and they're in a state of equilibrium, which is why the object eventually starts to like almost float. It doesn't go any faster eventually. It reaches terminal velocity. So in this problem, this little image here, it tells us like an entire story. So the whole story is that on the way up, the velocity was positive, but it's slowing down, it's slowing down, it's slowing down, and then it stops, and then it starts to fall, becoming negative, 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 more negative, more negative, more negative, getting faster and faster in the negative direction. Eventually, this would start to like almost flatten, and you would reach terminal velocity, and it would be a flat line. And the velocity would never exceed a certain value, whatever that is, depending on the shape, depending upon the density of the air, the velocity of the object increases or changes the air resistance. There's a lot of factors that come into play. The temperature that day would affect it. Yeah.
I just have a question about like that where you drop a penny from the top of the Empire State Building. Wouldn't it only do damage if it was on its side? Because if you're dropping it flat, wouldn't it like catch?
Well, Joe, that's part of the problem is that air resistance would never allow it to happen. So with air resistance, sure, you want to say like, if I drop it perfectly like this, right? You're saying like that, you just let go, like just open my hands, it should drop perfectly and go, it's going to tumble.
Yeah.
Air resistance is going to cause it to tumble.
And if it's flat, it won't just like hurt, but it won't.
Yeah, it would absolutely hurt someone for sure. They'd probably end up with like bruises or maybe even more damage, but it would not like embed into the person's head the way it's been described. Like it's like, you know what I mean? Like an axe going through someone's head or something like that. A spherical object has not the least, I shouldn't say that, has one of the least air resistances for object shapes if we're looking at just the overall shape. But if you looked at wings on an airplane, airfoils are shaped the way they are to create more lift or less drag and more lift, really. We'll get into that a little bit more. Does this make sense, this graph? You need to be able to analyze something like this and understand the connection. The image and the graph are really showing the same thing here. Okay, really showing the same thing. I didn't really even get into the word free fall or the phrase yet, but you have it defined here. So the way you think about free fall is when an object has no other forces acting on it. So, for example, if this baseball is no longer a baseball, if this is an airplane, and the airplane is taking off, I sure hope it's not in a state of free fall, right? If an airplane is in a state of free fall, that means it's like the motor stopped working and it's just going down. That's what an airplane in free fall actually means. So free fall objects simply mean that nothing else is assisting or hurting it. Air resistance we ignore for now. We're not going to include air resistance because it makes it what's called a differential equation, which is like an equation that uses the third level of calculus to solve in college. So for my first and second year of college, until we got into differential equations, we didn't even include air resistance in physics, even in college with engineering. It's a simplification that you make in high school and high school courses. I think in AP Physics, if you do well this year and you go on to take AP Physics next year, Mr. Donachek talks about air resistance later in the year, and he goes into it a little bit, which is really cool. But we're not going to get into air resistance because the math behind it is way more beyond what you've studied so far. Any questions? Okay. Let's look at this first example. Weird.
An object is dropped from the top of the Empire State Building, which is 443 meters tall, and lands directly below on the ground. Determine the velocity of the object when it makes contact with the ground. How long does it take to reach the ground?
So in this problem, we're doing what we just talked about, right? We're going to figure out that velocity. But what are we assuming? There's no what again? No what? What did I just say a minute ago? There's no air resistance. So is this object going to reach terminal velocity? No, it's not. Terminal velocity is reached when air resistance eventually balances out the weight and it just starts to coast and stays at that velocity. So this will get faster and faster and faster and faster in the negative direction. So in a world with no air resistance, with no air friction, that's what air resistance is, it's friction in the air. How many of you before in the pool have gone like this underwater? What do you feel when you do like this underwater? What do you feel? Resistance. That's a viscous force. It's a fluid that's causing you to feel resistance. It's the same thing you're feeling in air. You feel it differently though because the air around you, although it's a fluid, liquids and gases are both fluids. There is some resistance and you can feel it. You can feel wind on your hand, but it's not enough to really slow you down much, right? But when you do it underwater, you notice the difference? Imagine underwater resistance. That's what an object falling through space undergoes, or falling through, I should say, the Earth's atmosphere feels. The object feels the air physically pushing back up against it the whole time. As this falls down, air is pushing up. That's what you're feeling opposing your hand. So in this problem, we're going to assume for now, though, nothing is pushing back up on this object, so it's going to keep accelerating downward the entire time. Now, we need to talk about acceleration on Earth. So in tomorrow's lab, we're going to actually come up with a way to show a way to discover the value, and it's actually really, really precise. You know, remember how last lab some of the data we got wasn't exactly perfect? We had to use the boxes to make it better and stuff. This next one, the data we're going to get is like incredible how good it actually works. What it's going to do, though, is it's going to allow us to come up with the actual gravitational constant on Earth. That value, okay, you can jot it down. It's on your formula sheet. We call it g in physics, in lowercase g. And that's going to be negative 9.81 meters per second squared. So this is a value that we're going to want to use, and we're going to know it. It's on your formula sheet, so you don't have to memorize it, but I'm guaranteeing you. It's a Mr. Howell guarantee. If you don't believe me in a week, I promise you, come tell me, and I'll be like, really? In a week, you'll have this number memorized, easily. We use it in every single problem in this section. We're going to use it in every problem in the next chapter. It's the constant that is used on Earth everywhere. So negative 9.81 is something that you will memorize. You don't have to. It's on your formula sheet, but you will have it memorized eventually. Okay, so for now, take it on, my word that that is the value of acceleration on Earth. We are going to prove this tomorrow in the lab, though. Okay, so that's the value you want to start with. It's not given in the problem, right? Notice that? Acceleration isn't given. Because what's accelerating it down is gravity. I don't have to give that in problems anymore. Whenever a problem is falling, this is what you write down right away. Okay? This is in the vertical direction. We're looking in the vertical. Make that note if you want. We're not looking horizontally. We're not looking at an object like a football that's punted at an angle. We'll do that in next chapter. It's called projectiles. We are looking simply at free fall, an object that is falling straight down. Okay, right now we're looking at objects that are falling straight down. What else do we know? What else do we know? And this is where it gets a little bit trickier in this section. And don't even give me variables yet, just give me other information that's stated, and we can talk about what variable that is. So what other information do we know? All right, I agree. So let's draw a little picture, please. Here's our building, here's our object being dropped. The object goes down to the ground and eventually impacts the ground. The height of this building is 443. Okay, so that's my image. That's what I need you to be visualizing, right? That's literally what's happening here. 443 meter tall building where it's being dropped from the top. Now, we have to stop for a second and think about physics right now and forget thinking about common sense and pictures. Think about physics. What did I tell you about an object that moves to the left or down versus moving to the right and up? To the right and up we call something, and to the left and down we call another thing. What was the difference there? What did we discuss? Yeah, moving down is negative displacement. Moving left is negative displacement. Now, I'm moving down, so I'm going to call displacement y instead of x. Let's write a note here on the side. Okay, so I'm going to start by writing y equals, and I'm going to write negative 443 meters. I need you to write yourself a little note now, so later when you see this, you're not confused. X and y are the same thing in all these equations. It's just that now, instead of moving horizontally, I'm moving vertically. Again, in those big three equations we talked about in the last class, we talked about the big three. We talked about x equals VIT plus 1/2 AT squared. We talked about VF equals VI plus AT. And then we did VF squared equals VI squared plus 2AX. In all three of those equations, you can replace x with y when you're moving vertically. Is that clear what I'm saying right now? So y is my vertical displacement. And I'm giving it a negative sign because the displacement starts at the top and goes down. So it's negative vertical displacement. Joe?
Sorry, I almost repeat, but
Yeah.
like, if it's a vertical problem that has to do with free fall, then it would only be that. Like,
Correct. In the next chapter, we're going to talk about both horizontal and vertical at the same time. But I'm going one step at a time here. So we've done only horizontal up till now, right? Now we're going to do only vertical in this part. In the next chapter, we'll combine the two. Okay? So we'll eventually combine. But for now, we're not worried. Okay so far? All right, good. So I've got acceleration, I've got my displacement. What else do I know, or what else am I looking for? I need something else. And this is the tough piece that a lot of people forget. You won't forget it later, but because we haven't done enough of these problems yet, it's not as obvious. There's something else that's really important here. What about the velocity?
You need the velocity that it gets up to.
Okay, so either you need the velocity it gets up to, which is what it says, determine the velocity when it impacts the ground. So James, what variable would that be that we're looking for? Look at your formulas from the last section. Look at the last section, look at those formulas. Tell me what value or what variable that would be recorded as if I'm looking for the velocity at the end of the problem. VF. That's what I'm looking for. So let's put a question mark for that. Notice I left a little space here. Notice I left a little space. I have one other piece of given information still. What's the other given information that I do have? It's not obvious, but I have it actually. What is it? Good, very good. Because it's dropped. Let's write that down, please. I'll highlight it at least, actually. Whenever you see that, this is what you can write automatically, okay? An object is dropped. When that statement is made, you know that the starting velocity was 0. If instead, how many of you watched any football games yesterday? Anybody catch any of them? Okay. You must have seen a touchdown at some point in time, right? When anybody scores a touchdown, what do they do with the ball afterward? They spike it, right? That's an example where you do have initial velocity. Imagine that someone takes this ball and just spikes it into the ground. You're giving it velocity, right? So it would have some initial velocity. If I went to the top of the building and instead of going like this and letting it drop, and I went to the top and actually threw it downward, that would have some initial velocity. it would be negative because I'm throwing it down, right? If I took this and threw it straight up and waited for it to come back down, that would be giving it positive initial velocity. Throwing it down would be negative initial velocity. Dropping it is 0 initial velocity. Okay? So those are the 3 scenarios we have to keep in mind for initial velocity. It could be thrown up with positive, down with negative, or dropped with no initial velocity. Without that statement here, we cannot solve for VF. Without the VI equals 0, there's no way you can find VF in this problem. Now, we had 3 formulas. I need you to take those 3 formulas and think about them, but instead of x, put a y. In x's place, put y in its place. So I'm going to write them down so you can see them also. I'll jot them down over here on the side. So we've got this now. So the same formula except with a y. We've got this. Same formula except with a y instead of an x. And then the last one I don't even have to change. The last one is the same formula either way, because there's no displacement involved in the last one. So I'm writing down the same 3 formulas that we had in the last section, except instead of putting those 3 formulas with x, I'm putting a y here and a y here, showing that this is all for vertical motion. Same exact formulas. Anybody saved the formula sheet, I hope, earlier in the year? Can somebody open the formula sheet? How is it given on the formula sheet? With x or y? So we're all aware, so we're all clear of this. What do I got, Fiona? Yeah. On the formula sheet, you're going to see these formulas with x instead of y. You're not going to see them with y. I'm not going to give you the same 3 formulas and just change a variable. You need to recognize that when you're working in the vertical direction, all of your x variables become y. Okay? Now, which formula should I use to start? I want to find VF. I also want to find how long it takes. I want to find those 2 things. Which one do you want to start with? Anne, what do you think? With the last one? And what can you get with the last one, Anne? In this one here? If you know VI, A, and T, right? But do you know all 3 of these? Okay, so before you go to the last one, Anne, what do you think we should go to then? Probably the second one, because I know Y, I know A, I know VI, and I'm trying to find VF, right? So let's start with the second formula here. The third one we can use in a minute, right? Once we get the VF in, we know VF, we'll know VI, we'll know A, we can find time in the third formula. So let's use the second formula, please. Write down the second formula. If you feel like you've gotten good at this, you can go ahead and solve the second formula for VF. I don't even need the problem, by the way, anymore. Notice I can scroll off the problem. The problem's done. I've got everything written down. It's all math at this point. So let's jot down the second equation. And we're trying to find VF in this problem, right? Yeah.
Just a question. I know, like, for the purpose of this equation, it's probably really different, but would it technically the final velocity be 0?
No, so let's discuss that, Joe. It's a follow-up question I always ask. Eventually, the object hits the ground and stops, right? When a problem says the velocity, read carefully what it says, actually. When a problem asks for the velocity at the end or when it makes contact with the ground, that's called impact velocity. Let's write this down. That's a great question Joe asked. This is called impact velocity. We're trying to find the velocity, Joe, the instant before it hits the ground.
Oh, okay.
So imagine this ball is falling. It's like a millimeter, a micrometer, a nanometer from hitting the ground. It's just there. It has velocity still, right? Then it hits the ground and eventually stops, right? So sure, eventually the velocity is 0. But when it says find the velocity when it impacts or contacts the ground, we're looking for what's called impact velocity. And impact velocity is the velocity it makes when it hits the ground itself. When it hits the ground itself. I want to highlight that so you can see that. Okay, in green there, that's called impact velocity. It's never 0. It's always the velocity the moment before it hits the ground. Great question, Joe. Okay, I can't tell you how many students on tests answer with 0 sometimes because they think it's like a trick question. It's a quick question, right? It's not about the velocity eventually. It's the velocity the moment before impact. All right, so in this equation, we need to figure out what the value of VF is. Something that I like to do is I like to cross off anything that is 0 right away. What's 0 in this problem? VI. So the VI squared becomes 0. So go ahead and just go like this. Watch what I'm going to do. That's how I signify in physics that something drops off. I put an arrow through it like that, which means it goes to 0. You're going to see more of this notation in your pre-calc and calculus course you take. You're going to see this idea that an object's value goes to 0, meaning it's pretty much 0. It's no velocity. So this drops off. Question for you. If acceleration or displacement had been 0, what happens here? If acceleration or displacement are 0, what happens automatically? Good, because anything with multiplication with a 0 is automatically 0. Let's make sure we understand this. This is our zero product problem. 0 times anything is 0. So if any variable in a grouping is ever 0, the whole group itself is 0. Is that clear what I'm saying? Okay, I want to make sure our math skills are there for this. So we have 0 for VI, so I can rewrite this equation on the next line as the following. Because VI is 0, it's gone, it doesn't matter. So VI drops off. Now I just have to solve for VF. How do I get VF by itself? What command or what action do I take at this point? There's only one thing I can do here. Right? There's literally one thing I can do to get VF by itself. Square root. We know that square and square rooting are inverse operations, so we can square root it. What do you remember I'm a stickler about? Some of you should remember. Very good. And it's really important right now. Think about why it's important right now. Who can come up with the answer to that before you get a number? Don't even give a number. Why is it really important for this specific problem to be putting the plus or minus there? Come on, use your context clues. Think about what you're solving for. Will?
It's falling, so the velocity is going to be negative.
Yes, it's moving down, isn't it? This object was dropped. So its velocity becomes more and more and more negative. So our final answer for VF, the velocity when it hits the ground, should be negative. So in this problem, we should be looking for a negative answer. So this is one of those times where we have to make sure that we put plus or minus. We always should, but specifically here because of the fact that this actually turns out to be a negative answer. So now I just plug in. Acceleration is negative 9.81. Displacement is negative 443. I should put units for now. I'm dropping them to be careful, or to be quick about it, I guess I should say. Okay, it would be meters per second squared times meters, which should be meters squared per second squared. I should show them. Let me show those real quick, sorry. I'm just going to put the units back so you guys can see the units analysis. So this would be meters per second squared, and this would be meters. Why am I doing that, by the way? What do you notice? What do your units become under the square root? What do your units end up becoming?
Second squared is
Careful. Meters would cancel if you had top and bottom, right?
it would be meters squared
Over.
seconds.
Yeah. Underneath the radical is going to be meters squared over seconds squared. 2 times 9.81 times 443. Anybody got a number for me just so I can write it down for now at least? What do you got?
8,691.
Thanks, James. And the reason I asked for that is only to prove the units. Eventually, I'm not going to ask for that number in the middle. You can do all the work yourself, right? But take a look. What should my units be for velocity? Think back to velocity. What have the units been? What's the standard unit for velocity?
Meters per second.
Meters per second. But I don't have that, right? I have meters squared per second squared. Why does it make sense, though? What am I doing to this operation? Yeah, I'm taking the square root of this number, aren't I? I'm also taking the square root of the dimensions, really. So when you square root meters squared, it becomes meters. When you square root second squared, it becomes second. the answer makes sense. It should be meters per second. Okay, I'm going to put this little symbol meaning what again? What does that symbol at the bottom mean? Approximately. Okay, approximately. So I'm getting an approximation for my answer here. That approximation should be around 93.3 meters per second. And I'm going to put a negative because it's moving down. Okay, approximately negative 93.3 meters per second. Jeff?
So you get m squared because you're multiplying m with m, right?
Yep, and the second m is really over 1, right? See the 443m? That m is over 1. So it becomes m over s squared times m over 1. M times m is m squared. S squared times 1 is still s squared. Yep. Okay, this is the velocity of impact. We still need the time. Almost there. I know, we're almost there. We're finishing one problem. See how long one problem can take? I'm stepping you through it. On your homework, you're eventually going to be able to do this in like 5 minutes. But I'm trying to go deliberately slow. Tomorrow we're going to do 2 problems in probably about 20 minutes to start. And then we're going to spend 20 minutes on that second part with the lab. So we're going to go a lot quicker tomorrow. I'm not going to stop along the way as much as I'm doing it now. How would I get the time? How would I get the time? Because now I've got a lot. I've got VI, I've got VF now, I've got acceleration, I've got displacement. How can I find time? What do you think, Andre?
Use the last one.
Which is?
VF equals VI plus AT.
I agree. This would be the easiest formula to use right here. You could use the other one also. You could use y equals VIT plus 1 half AT squared. Drop off the VIT because the VI is 0. Find t squared, square root it. It's a lot of work, right? So I would prefer to solve for t here. If I'm going to do this with all variables, if I want to get used to it the way I've been showing you guys, I would start by moving VI over. Okay, remember on the side, think of these as numbers. Imagine this was 5 equals 8 plus 2t. How would you solve that equation? You would move 8 over first. By subtracting 8, you would move it over and then divide by 2. So subtract VI and then divide by A. This will give you the time that you're looking for. Because now it's useful that I can just simply plug into this equation. Again, solve this the same way you would solve what's on the right there if you're having trouble with this still. If I plug in, I can plug in my final velocity of negative 93.3, which I just solved a moment ago, minus initial velocity all over acceleration. It'll give me a time of approximately 9.5 seconds. Okay, 9.5 seconds. So tonight, you don't have actual homework tonight, but if you look at Moodle, you'll see that your homework from 3-4 is due on Wednesday. You can start it tonight. You have more than enough tools under your tool belt here to actually assess one of these problems correctly. Okay, go. I don't want to get this. Thank you for not jumping out of your seats. I appreciate that. Joe, you had a question?
Yeah, the question was, you always want to see your exact approximation.
All right, so a toy rocket is launched with an initial velocity of 25 meters per second straight upward. Okay, so it's launched upward, not left to right. After how much time will the rocket reach max height? And then 3 more questions. I gave you these questions in order. What do you think you probably would do? What should you probably do?
Solve the first one first.
Yeah, they're going to probably lead step at a time. I talked about this the other day, some of you might go on to take AP Physics next year. If you decide to, on AP exams, this is how they're set up. There are like 4 or 5 parts to every problem, and each part affects the next part. So the first answer is going to most likely affect the second answer, et cetera, et cetera. So you need to be very careful, right, on those kind of exams that you do well in the beginning. Now, I want to point something out. On my tests, listen carefully to this. If you don't know the answer to A, and you have no idea what to do, but you can get B, pick a number for A. It says how much time will it take to reach max height, right? You can't get it. Let's say, for example, you just forget how to do it. Say it equals 5 seconds, and I'll mark it wrong. Don't even put words, but t equals 5 seconds. Or you can say let t equal 5 seconds. So at least you can still do parts B, C, and D with that number. Does that make sense what I'm saying? So if you can't get part A, and A affects B, put a number for A, and if your work is all correct for the successive parts, you'll get credit for those parts for sure. You just won't get credit for the first part you couldn't do. So whenever a part stops you, give a number for it and make it a reasonable number, obviously, right? Like time shouldn't be negative or something kind of thing, right? Yeah.
You're looking more for us to like understand the process of it for the question.
Correct. Well, the next question is going to be impacted by the first one, is what I'm saying, Joe. So if you have trouble with the first one, but you can show me that you get the process and can do the math, you got to still do all the math. So parts B, C, and D have to be correct based on your number you chose for A. Okay? So no double jeopardy is what I'm saying, pretty much. So after how much time would reach max height? What did we say yesterday about max height? I had you write it down. I told you to write it down. What happens at max height? Chris?
It stops.
Very good. It stops. Because it stops, what can I say about the velocity at max height? It's 0. So let's draw a picture of this diagram. We want to know only from launch to max height for part A. So do I care about it coming back down? Not right now, I don't. Not right now. So let's draw a diagram on the side if we need to. Okay, here's the rocket. I'm just going to draw a rectangle. The rocket takes off, gets up to max height. That's the end of the problem right there. So here, the initial velocity was 25 meters per second. So I'm going to call this the end of the problem. So the beginning of the problem, the velocity was 25. At the end, the velocity is 0. The problem in my mind only exists from ground to max height. I'm truncating. Remember I used that word the other day? I'm breaking the problem into pieces. I'm looking at it from the ground until it reaches max height. For now, for parts B, C, and D, I might change that idea. All right, so I know those two pieces of information. What am I looking for? What am I looking for? What variable? Give me the variable. Give me the variable. Someone besides James, you just answered the last one. What variable are we looking for part A?
T.
Thank you. T. We are trying to find time. It looks like we don't have enough information. VF, VI, and T is not enough. I can't solve for time in any equation unless I know one other thing. What's that one other thing we do know? What do we know?
Acceleration.
What is it?
Negative 9.1.
-9.81. Yep. It's fine. -9.81 meters per second squared. Okay, acceleration on Earth due to gravity. Gravity is what's causing that acceleration. Now, with those 4 variables, I'll give you, 30 seconds. Look at your 3 formulas. Go to the last example from yesterday. You can see all the formulas if you wrote them down. Look at your 3 formulas and pick a formula that you want to use to find time. You got it already?
Would it be the last one?
Read it out for us.
VS equals VI plus AT.
Okay, so Fiona thinks it's this one. Can somebody either argue with her or agree with her and give me a rationale? Go ahead, Will.
We do A equals change in V over T.
A equals change in V over T. Now, inherently, you remember those are the same formulas. So you're both answering with the same answer. These are the exact same formula because delta V is VF minus VI, and that turns into this formula. Remember that? So these are actually the same formulas. So either one works. Why does either one work is what I was kind of asking. Can somebody affirm that these are the correct formulas? Why could I use either of those formulas? What do you think? You answer your own question.
It's easy to get T alone from both of them.
Yeah, you could solve or isolate T. That's one reason, Fiona. There's a second reason also. James?
I was going to say, in the end, you're just basically dividing.
Yeah, so that makes it very easy. But I mean, physically, why are you allowed to use these formulas? Come on. I had you list everything else, right? So what do you know? You know VF, you know VI, you know A. So you know VF, you know VI, you know A. What's the only thing you don't know in that equation? T. That's why you can use that formula, okay? So we have to understand how to choose the correct formula. The majority of issues last year came about from 2 things. 1, understanding the problem, like literally writing the givens properly. 2, picking the right formula based on the givens and the desired variable. But this is the process I have you use on the problem sets for a reason. So when you have a math problem for the problem set, when you have problems with the problem set that are like explain why an object stops at the top of its path, you don't have to use the statement like desired variable, givens, obviously. For the math problems, use this approach. Listing your givens, the equation, and what you're looking for. All right, VI is 0. That drops off. I'm going to put a 0 through that. I'm going to go ahead and slide this down a little bit so we can see a little bit better. If I solve for t, it becomes VF over A. Again, drop off. This is annoying because I can't cover stuff up in my hand. So cover up the VI, because VI is 0. So in your mind, cover this up. Okay, it's gone. So you just get VF equals AT. So divide by A. So as James said, it's just 25 over pretty much 10, or close to 10. Oh, I'm sorry. I put VI as 0. I got it backwards, guys. Backwards. How come you didn't raise your hand? Raise your hand, please, if you see me making a mistake. Don't let me continue it. There we go. So it's VF that was 0 because it stops at the top. How did I recognize my mistake there, by the way? Anybody pick up on it? What would I have gotten as an answer for time? What kind of a number? It would have been negative, which was my indicating factor that clearly I said VI equal to 0 accidentally. Do you see how you make corrections on your own work? It's actually not bad that that happened because you need to see that kind of thing. On the test, when you get a negative time, it means what? You made a mistake somewhere along the way. And that's what I would have gotten as an answer because I originally set VI equal to 0. So yes, VF equals 0. I apologize. So let's move VI over. So it becomes negative VI by subtracting it over here. And that equals AT. Then divide by A still. And now my answer is negative VI, so negative 25, because VI was 25, over negative 9.81, which is A. And what will that give me as a time? What do I got? Again? About 2 1/4?
Yeah, 2.55.
2.55. Okay, about 2.55 seconds for this rocket to reach max height. Do we know what the max height is? Yet? No. Can we calculate it? Sure. We can do that. Let's take a look at what Part B asks of us. Part B says, oh, look at that. What is the rocket's max height? What is the max height? What variable are we looking for when we look at the rocket's maximum height? What variable? And be careful here. It's not H. The maximum height of the rocket, what physics variable do we use to measure how far something goes in this direction? Why? The vertical displacement is what we're looking for here. So the question is, what is the Y value for part, so this is part A. Part B we'll do over here. What is the Y value is the question. We didn't have to use this, so let's just cross it off so it doesn't confuse us. What is the height? Formulas. 2 options. Which one should I use? Katie, which one do you think? Does that work? Do we know A? Do we know VF? Do we know VI? We know everything. We can absolutely solve for Y. Can I use the other formula if I wanted to? Sure. Here's the other one. I know everything else there. So let's do this. Here, ready? Since Katie recognized the first one, this half the room, use the first formula, please. You guys over here, use the first formula only, please. VF squared equals VI squared plus 2AY. Plug in your givens and solve for Y. Come up with an answer. Over here, do it with the second formula. Okay, VIT plus 1/2 AT squared. I'll do it for both. Again, we're only looking at the first half of the trip. The rocket has not come back to the ground yet. So VF is still 0 for those. So for those on this side of the room, if you want to solve generically, check your work on what I put on the board. Over here, you don't have to solve generically. It's already solved for Y. So this side is a little bit easier. So I'm splitting it down the middle here for the 2 methods. If you use this method, you don't have to actually do anything. You can just plug right in. Be careful, by the way. Please look at my work for those on Katie's side of the room over here. The negative is on the outside of the square. You square 25 first and then negate it. You see what's happening there? This symbol actually means the opposite of. It's not really a negative sign when you think about it mathematically. A lot of students are going to square negative and make it a positive. Your answer wouldn't make sense. You'll get a negative displacement. Okay, because this is going to be over a negative number. Make sure your denominator has parentheses around it if you're going to put this in the calculator, or just use 19.62 instead as a negative. You can't type that directly in. You need a bracket around the denominator so it does the multiplication in the denominator first. If you're going to type this in your calculator, put an extra bracket around your denominator when you type it in. On the right-hand side, those on this side should be easy to get. What do you get? What do you get? Yeah, what do you got, James?
About 31.86.
Let's see how close it is. And they're going to be a little bit different because the methods are different. One involves a square velocity, one involves a square time. Because we rounded time, there's going to be rounding errors involved here. James got around 31.86. That looks about right.
I used 2.54
You used 2.54? Okay. What did you get on your side over here? Anybody get the calculation? Yeah. And I had 31.85 in my notes because I used the method on the left. So there's definitely going to be deviation, but it's very minuscule. Okay, so the answer for part B is around 31.8586-ish. No matter which method we use, that's kind of interesting, right? That you can use multiple formulas to come up with the same answer. It's actually almost kind of crazy when you think about it. What are the odds they happen to work out? The reasoning behind it is that these formulas are all related to each other. The reason that they come about all come from a little bit of calculus work. And those all stem from the same governing principles. That's why you can use either one. What does part C say? What does part C say? Wherever you go, what does it say?
Why would its velocity be when it returns to the ground?
Okay, so when it returns to the ground now, right? So if we wanted to return to the ground, we could either do one of two things. We could look at the whole problem, or start the problem over at the top and only go to the end. So look at the second half of the problem. You follow what we're saying here? What that means? I could start from the very beginning with initial velocity of 25, get it launched, come back around. We'll do it both ways. Or I could start as if it's being dropped from the top, because doesn't it stop at the top? So it's like, it's pretty much a free fall from the top down. When it gets to the max height, after that, it's just a free fall falling down. So let's do that both ways for part C. Oops. Okay. So this is part C we're on now. Let's take a look at both solutions. So top down, and then full problem. So in the first one over here, we're looking at if it's dropped, imagine it hits the ground. And over here, we're looking at what if it's launched, it goes up and comes back down to the ground. Okay, from the top down, as it's dropped, and then full problem. Let's do top down first. Okay, let's do top down first. Now the key here, though, is that, again, we got to get the same answer, right? So whichever method you want to choose is fine on the test. For now, I'm having you do both just to practice a little bit. So top down, what would the initial velocity be for this problem? If I start the problem at the top, what's the velocity initially now if the top is the beginning of the problem? N. 0. The velocity right here is 0. Now I'm going to call it VI. This is a new problem, right? We're now on part C, which could utilize part A, but it doesn't matter. So I'm starting the problem at the top. So I call the top VI, which is 0. If I was starting on the other problem, VI is still 25. Because the beginning of the problem over there is from the ground when it's launched, and when it's launched, that velocity is 25. So I can interpret this both ways. On the left-hand side, top down, right? We want to figure out what the velocity is at the end. So what else do I know? What's the displacement? What's the displacement? Will?
31.86.
It's going down, Will.
Negative 31.
Very good. How about for the full problem? If I start on the ground and end on the ground, for the right side, right now we're on the right side. If I start on the ground and end on the ground, what's my vertical displacement? 0. So see how these problems are different? We're going to get the same answer for part C either way we do it. Because at the end of the day, we're trying to find the velocity right before it impacts the ground, which is the same on both sides. Now, mathematically, I need more information. I'm looking for VF over here. I know acceleration in both cases. Okay, acceleration in both cases is the same. Can we come up with a formula we're going to use in both cases to figure out what VF is? What do you think you want to use, Rodrigo?
So VF squared equals VI squared plus 2AY.
I would absolutely agree with you, Rodrigo, because it's already solved for VF. Well, square rooted, obviously, but it's pretty much solved at this point. On the right-hand side, I would use the same equation. But your givens and what you're going to plug in are what are going to differ. So over here, we get VF squared equals, this is 0, VI in this first one, 2 times A times Y. So VF equals the square root of whatever that is, which is some number. And that's in meters per second. And we know it's plus or minus because we're taking a square root. So that's the left-hand side approach. Let's look at the approach on the right hand. I'm not even getting a number yet, notice. I don't even care about the number, I just want to see the approach. Okay, take that approach on the left-hand side because it was dropped from rest, so VI is 0. But on the right-hand side, what's 0? Katie told us, what's 0? Over here, if I look at the problem, from the ground to the ground, what's 0 in this part? Just read it. What's 0? People, besides Katie, what is it? What's 0 here? Yeah, the displacement. Because if you look at the problem starting on the ground and ending on the ground, there's no displacement. So you can drop off the right-hand side of that equation. That makes that equation real easy. Or the right-hand term. That whole thing goes out. Because 0 times anything is, thank you, 0, right? So 2 times A times 0 is 0. So that whole thing goes away when I solve it that way. So if I look at this method, VF will just equal whatever VI is squared, which is 25. So VF is equal to plus or minus the square root of 25 squared. Well, what's the square root of a square? What happens? Yeah. So what's the answer? The answer is just plus or minus 25. And if I do the math over here, I'm going to get around around 625 under the radical, which will give me plus or minus 25. It's not exactly 625. What is it?
625.00.
So it's darn close, huh? Okay. So this is around 625 and change right here.
And a 0.09.
0.09. So 625.1 right here. Okay? But I want you to see that it's the same answer in both ways. Now, is the answer negative or positive? 25. Use the context of the problem to answer. Is it negative or is it positive 25? Which one of them could it be? Ricky?
Positive,
Why positive, Ricky?
because it's going up,
Is it going up, Ricky?
but then it's dropping.
And we're trying to find the velocity as it's about to hit the ground.
Oh, negative.
Good. All right, so at least you rationalized it correctly. So it was coming down, right? So we're looking for impact, not initial. We're looking for final velocity, which we can call the impact velocity, the velocity right before the rocket hits the ground again. And that's going to be negative. So our answer for part C is just negative 25. It is the same as the initial velocity. All of the energy that the rocket lost on the way up to gravity, it gained on the way down to gravity. This is a rocket that doesn't have a propulsion system. This is like, ready? I took a baseball and threw it straight up. As soon as I let go, what's the only thing acting on it? As soon as I let go, what's the only thing acting on it? Gravity. It loses energy from gravity on the way up. It stops. It gains energy from gravity on the way down. The same amount of energy it gains and loses, it gains. So although it loses 25 meters per second, it also gains 25 meters per second on the way down. That's why the initial velocity was 25 and the final velocity was just negative 25. What is this assuming we're ignoring or neglecting? What did we talk about last class? We neglect something. Air resistance. If you actually throw a ball up in the air, it will not come back down with the exact speed it left. Okay? If you throw it upward, it's going to lose a lot of energy on the way up due to air resistance, and it will actually lose some energy on the way down. It will be less velocity on impact than it was upon release in real life. This is assuming no air resistance. That's why the numbers are perfectly even and symmetric at 25. Part D says, how long will it take to return from max height to the ground? What do you think?
It's the same time as to go up.
Yeah, 2.55 going up, right? And if we're really pushing symmetry here, right? With the 25 meters per second piece. So it should be symmetric. So it's probably 2.55 down. But you know what? Let's prove that. We can prove that easily. We can prove that using top-down method. Or we can prove that using full problem method. I'm going to use top-down method. Okay? If I continue part D, and I'm going to continue part D using top-down method, I could think of this. So here's part D now, from top-down method. I could say that VI is still 0. VF is now negative 25. We know that. We just solved it. I'm using the previous answer, notice. A is negative 9.81. Y is negative 31.86. And we're looking for T. I can use multiple formulas here. I can use multiple formulas. Which one do you suggest I use? There's more than one right answer, but one answer is better than the other. There are multiple ways to do this, but one way is more efficient than the other. What formula should I use to find T? Same hands, same hands. Come on, I know others of you know these answers. Get those hands up. Katie, go ahead. I agree. I think this is the simplest formula because you know what? T is by itself, kind of. It's not squared. I could use y equals VIT plus 1 half AT squared, but then I got to take a square root of T later on, and it just becomes a messy problem. Okay, solve for T. We know that VI was 0. That drops off. We're going to get 2.55 for sure. Thank you. Final velocity is negative 25. Acceleration is negative 9.81. Divide those two, you will get 2.55. And that's again proving, as Rodrigo showed, the symmetry in the problem that exists. 2.5 seconds up, 2.5 seconds down. Because there's no air resistance taken into account. Joe?
So a lot of this is just finding the right formula to use?
Yes, that's exactly it, Joe. That's all this is in physics this year. This is the beginning of it. So I'm not going to lie and say it's not going to get harder. It'll get harder. When we do two-dimensional projectiles, it will. But you know what? Your next test is all going to be Chapter 3, one-dimensional, and then it's going to be, we're going to start the beginning of what are called vectors. It's not going to be motion yet. The next test will be on that kind of stuff with projectiles. So right now, you have to focus only on one-dimensional. This is the easier version of motion. When we get to two-dimensional, I think it gets easier because you're doing more of it, but it incorporates more stuff. So it's a little bit more difficult in the idea of context. You need to know more. But you're doing it a second time and a third time, so it gets a little bit, I think, easier naturally. Okay? This is a long problem, right? 4 steps. Periods 11:29, right? Can we start the next one? You have a question? Go.
When for part B we solve for y, I was wondering why we use y.
Because we're looking at vertical displacement when we look at a height of something, right? So if it starts at the ground and ends up here, I would call that y or h. If you want to use h, it's fine, but I call it y. It's like calling x instead of d. X is really displacement, right? D is distance. H is really a distance in a sense, whereas y can be positive or negative. So notice in one of the problems, y was negative here, wasn't it? Because the object started at the top and it fell down. So y is a vector. We'll talk about vectors soon, but it indicates the direction being up or down, whereas h would only be positive. It's like D, okay? Take a look at this last example here. So This one is going to involve you using the quadratic formula. Okay? I recommend highly that either you learn it well, learn how to use your graphing calculator to find the x-intercepts, which is the same thing as the quadratic formula, the x-intercepts. Or use the quadratic formula program. You can write a program that does quadratic formula. It's actually allowed in the SAT now. So I don't mind if you have a quadratic formula program in your calculator. If you have other programs in your calculator, I will get very upset. But if you write a quadratic formula program, you just have to enter A, B, and C. I can even send you guys the literature on it. It's very easy to write a program on the calculator. So I'll send you how to write a quadratic formula one if you want. All you got to do is type in what A is, what B is, what C is, hit enter, and it does all the work for you for the quadratic formula. Very useful for like an SAT type test. Okay, not useful on a math test where you have to show your work, right? But for physics, for this, if you can get the governing equation and you use the program to get the roots, that's fine with me. If you factor, you're not going to be able to factor, so forget factoring. If you use the quadratic formula written, fine. If you use the x-intercepts, that's fine. I don't care. Any of those work. Okay, take the shorter route for now. So Jason hits a volleyball, initial velocity of 6 meters per second. It acts straight upward. So right away, list this, right? Right away, list this. That's our VI. If the volleyball starts from 2 meters above the floor, how long will it be in the air before it strikes the ground again? So let's draw a picture at this point then. Let's make believe Jason is a setter, because 2 meters above the floor is about 6 feet. I need to think about the reasonable nature of these numbers, right? Here's 2 meters, right? You're about 2 meters, a little more, really, you? Right? Taller than 2 meters? 6, 7. Is that what 2 meters? Yeah. So he's hitting the ball from about here. So this is where the ball is initially. So the ball is above his head, or at least in this area. The ball is going to go up and come back down and hit the floor. I need you to visualize the motion occurring. Where is the beginning? Where is the end? That's what's important here. Does this problem ask me anything about max height? Look at the problem. Anything about max height? Does it ask for the time to max height? Does it ask for the distance or how high up it goes? Does it ask either of those things? So do I care about the first half of the problem like I did last time? What do I care about? I want the time it takes, I think, right? Until it strikes the floor. So I care about from beginning all the way until the end. So I don't need to break this problem into pieces. Does that make sense, what I'm saying right now? I don't have to start by automatically breaking into pieces because I'm not interested about max height. I'm interested in the full problem. What is the overall displacement? Starts here. Listen, watch what I'm doing. Starts here. I don't care the path taken. Ends on the ground. What's the overall displacement? The overall. Same 2 hands. Joe, thank you.
2.
Be careful, Joe. Starts up here, ends down there.
Oh, okay.
So not 2, but help him out. Not 4. -2.
Oh.
Think about it, right? You're starting here and ending here. So in essence, although the ball goes up and comes back down, the overall displacement from beginning to end is which way? Which way? Answer the question. Down, right? Starting here, ending there. That means even if I went up, even if I went out, I ended up down, below where I started. So the vertical displacement is -2, meaning 2 meters below where it started. Okay, 2 meters below where it started. That's why you have to remember what displacement means. It means the change in position. I went from up here to down there. That's a loss of 2 meters, -2 meters. I don't care if this ball went 70 feet in the air or 2 feet in the air. It ended up 2 meters below where it started. That's what matters. Agreed? Okay. Do I know VF? Do I know the velocity, the instant before it hits the ground? Is it given? No. So I don't write anything for that. Am I asked for that? No. So let's leave that alone. So let's leave VF out of this for now. For now. What do I know that I have to always know for all these problems? Very good. Okay, we have to always start by writing these down when there's vertical motion occurring. And we're looking for time. So unfortunately, I don't know VF. I can calculate VF if I want to, and then use another formula to find time. That would involve 2 formulas having to be used for one problem. I can do that. So I can right now use VF squared equals VI squared plus 2AY. Calculate VY. Then use VF equals VI plus AT to find T. I don't want to do that. That's two entire separate formulas. So let's use the formula that involves all this. What formula are we using then? What's the other formula I didn't mention? Go.
Y equals VIT plus 1/2 ABT squared.
Good. This is the one time I will tell you, write this down, you're not going to solve generically. Because where is T? Is T in one spot? Where is T? It's in two spots. So you can't solve for T in this problem. It's not possible to get T by itself. So in this problem, instead, plug in. And then let's work through this to make this a quadratic that looks nice. Half of 9.81 is 4.905. It's a negative. So I'm going to write it like this. Watch what I'm going to do to make life nice and easy for me. Okay, use decimals with the coefficients here. All I did was half of 9.81, and it's a negative, so I write that as a minus. I can move the 2 over and put everything in order. $6t has a positive in front of it, and the 2 when I move it over is a positive. Remember, I'm going to add 2 and add 2 over here. And I'm going to switch the order so that it's in standard form. A, negative 4.905. B, 6. C, 2. Either use the quadratic formula to solve this, or use a quadratic program, or plug that into y1. Take a look. This is another method that a lot of you haven't done ever. Plug this into y1, where you see a t, call it x, and then find the x-intercepts. The x-intercepts are the zeros of a function. What makes the function equal to 0? So you could gladly find the x-intercepts on the graph. Okay? For the sake of time, because we have a minute right now, okay, we have a minute, I'm going to show you the 2 answers you're going to get. You will indeed get 2 answers here. Which answer am I going to use? Negative 2723 or 1.5? Which one? Which one? Chris, what do you got?
1.5.
Yeah, because?
It's, you can have negative time.
Correct. You know what the negative time would represent? I'll give you a little quick thought about it. He hits the ball upward, right? It would be if it was like reverse motion coming back to the ground. That's why you're getting that second time there. Okay, it doesn't matter for the sake of this course. It doesn't really matter ever, actually. Okay, the positive time is the answer we're looking at. So it takes about 1.5 seconds to get back to the ground. If you don't know where those answers came from, tonight, listen carefully. In addition to your homework, you don't have to do this and turn it in if you don't want. I will put up some practice problems with quadratics. Just practice quadratics, please. Okay, either you are using the quadratic formula, you are using the quadratic program, I'll send you that also, so you can input in your calculator if you want to type a program up, or you are using a graphing calculator to find the x-intercepts. If you don't know how to do that, I'll also put a link to that. There's a quick short video that I put up every year. It's not even one I did, I just found it on YouTube. It's very simple to find the x-intercepts on a graphing calculator. Okay, it's a command on there, so please look into it. All right, tonight, 3-4 homework, please, right here. Okay, it's listed right here. Please make sure to do the correct problems.